Today is a discussion on finding evil using TLS, but TLS is a freaking beast in that you've got the older SSL versions, you've got TLS up to the newer 1.3, and quite frankly, politics and regulations around the world, which I think privacy is important, especially as an individual. But as a business owner, I absolutely don't like it because it's not about monitoring my employees, but it's about being able to protect my organization and my employees and my customers. Now, I'm specifically talking about technologies like TLS inspection and decrypt port mirroring. And for the vast majority of the world, the answer is no. So Bryan's got this pretty cool project he's been working on. I read his gold paper for SANS. And historically, I kind of beat on machine learning because, well, I like it, but I hear so much vendors pushing for it. And I see a lot of my clients buy it, but they have no clue what to do with it. And therefore, they own a capability that I argue isn't a capability because they don't know how to use it. So Bryan's got this nice write-up. He's going to do a little bit of demoing today. He's going to talk about it. And Bryan, are you a data scientist?
No, not at all. But I play one on TV.
Oh, see, there we go. There we go. I from talking to him on this, and this is why I wanted to bring him in, like he put a really cool project together with enough information that I feel it could be applied as an actual use case. Like people can adopt this and use it. He's got the GitHub project, so everybody has access to everything. And I'm going to let him talk through it here in just a little bit. But I loved it because he basically went from zero to what I'll say hero, right? Bryan, you're my hero. Because he learned this from scratch. Like this was part of your master's program, right?
Yeah, the SANS Information Security Engineering program. So
yeah. And I don't know why you picked this. I think you told me last time. I'll re-ask you that probably later, but why don't you tell us about the project a little bit?
Yeah, so well, first of all, to answer it, even though you haven't officially asked the question, I didn't pick this. I didn't pick the machine life, it picked me. Anyway, so it originally came about as a conversation with Don Williams. If you've ever taken like Sec 503 or any of that kind of stuff with SANS, he's one of the principal instructors for that. So anyway, we were having a conversation about just analyzing TLS traffic, the things that you can learn just from looking at statistical analysis of it, understanding connections at a low level, what a standard TCP connection or web connection looks like, and that kind of thing. And building a platform around just performing that analysis and using like Grafana for time series analysis and things like that. So you can look at the difference between, say, a TLS connection, like a normal web connection is going to be a small request out to a web server, big response back as you're downloading all of the images and other data from the server. Well, a C2 connection may look exactly the opposite. And in many cases it does, where you've got a small inbound connection, which is your command to the system. And then you've got, maybe if they're exfiltrating data, you've got data that's leaving your network. So it looks exactly the opposite. So the idea, the brainchild behind it was there's got to be a ways to just statistically analyze this data to help an analyst figure out what's going on. Is something potentially malicious or not? Then in talking with my research advisors and stuff like that, they said they didn't want a platform for it. They wanted it to be more like researchy oriented, if that makes sense. And so it was brought up for building something in machine learning to allow the machine to make some of those decisions instead of leaving that decision-making process up to the analyst. So something to assist in that determination instead of it's, hey, analyst, here's what's going on, you figure it out. So that kind of led me down the machine learning route. I've always wanted to learn about it. And so I said, sure, why not? Let's do this. So that was kind of how it all came about. Outside of that, essentially what I'm doing is looking at just the TLS header data or that the handshake data to look for differences or to look for anomalies between a normal TLS connection, say to google.com, and a malware, say a C2 connection or something like that. So just to, initially it was just to look at, is there any difference that can be that can help us make that determination. And then once I found out that there were enough differences, then I started kind of modeling the machine learning algorithms around that. So,
sure. So how does this difference, how does this you know what I'm saying?
Differ?
Yeah, differ. We'll go differ, right?
Yeah,
How does it differ from things like, say, like a JA3 or JA3S fingerprint?
Yeah, so the JAW3S fingerprints, I mean, those are great. Well, aside from the MD5 limitations of JAW3 and JAW3S, right? So, you know, you can have the same fingerprint, which is what they're creating from this for any number of connections. So a Chrome browser may look exactly the same as the Windows Update service. You know, the JAW3 handprint may be exactly, or fingerprint may be exactly the same. And there's no way for you to know that. So there's a lot of potential for false positives. Cisco actually came out with a tool called Mercury that helps to mitigate some of this. And they generate a much more complex fingerprint where they take a lot of those values that instead of like generating a single MD5 hash from it, they actually generate some like hex values for each of the different aspects of that TLS handshake. And then you have to correlate that with their database that they've captured and put together. So you're limited on what they can and can't do or what they have or haven't done over time. And so I wanted something that was going to be, for lack of a better term, smart enough to be able to put this together and help the analyst based off of their network and their environment. So
now you've mentioned that multiple times, that you want basically the computer to find something for you, but with the analyst to consume and use the information to figure out what's actually going on. Which I find the fact, because you didn't do that the last time we talked, and I love that because I'm used to the opposite. I'm used to someone saying, buy this, it will find the anomalies for you, go. And it's like, I mean, everybody's heard of alert fatigue, but nobody's really talking about anomaly fatigue, which is probably 20 times worse, because an anomaly is not an alert. It's just a, hey, not normal.
yeah.
Well, this is tea in the morning, that's not normal. This is coffee in the morning, that is normal. So I have one anomaly and one normal, and nobody cares.
Right.
So I think it's interesting that you're verbalizing it that, because I feel like machine learning today, and I'm not a data scientist, I feel like it's one of the best enablers. Maybe best isn't the right way. It's the most, I'm trying to figure out how to word this without sounding too pitchy. Like, it's way more mature than it's ever been.
Yeah, no, definitely.
And so if you know how to use it, and you do, and you're maturing as an organization, it can be a humongous enabler.
Exactly.
In retrospect, I think most organizations aren't ready for it, but
No.
those that are can now open doors they never could have before.
Yeah, it's interesting. If you look, DoD is placing a renewed emphasis on AI machine learning. They've actually had this whole new initiative come out, and they're supposed to be creating these AI teams, like machine learning teams, to figure out how they can best leverage that technology. I feel like, you know, there was actually a LinkedIn like survey kind of thing that went out this last week talking about it, and they were asking the community, like, what do you think they should do? Should they, you know, and there's like 3 different options. Should they, you know, inform leaders, create teams, or, you know, just leave this up to the greater, you know, greater community, commercial community to figure out? And the bulk of people said they need to build up teams. I disagree. I think you have to inform leaders first.
So that's actually what I would have said. Absolutely not number 3. You probably should start with 1 and then go to 2 after.
Exactly, because you have to inform leaders on how this can help them. And then once you've informed them, then they know how to build teams to solve their problems, because they know that bigger
picture.
And
I would caveat that one more way. It's how it can help them and how it can actually hurt them or not help them.
Yes.
Because you have to weigh both sides of that.
Yeah, exactly. And one of the things that I did with mine that's different from a lot of the other ones that I've seen, they try to get so deep into the weeds that they're not only trying to find malware, but they're trying to specifically classify malware families, right? And I mean, I can understand the help in that, but at the same
playbooks or 300 playbooks.
Yeah,
I vote 5.
Yeah, exactly. And so I just went with mine with a purely binary decision. Is it anomalous, right? Is it potentially malware, or is it normal traffic? And then from there, the analyst can do the deep dive. Right now, I can look at PCAPs or flow data, and I can look at whatever I need to figure out, look at IDS logs or SIEM logs or those types of things. But this can be, I'm a SOC analyst, and I come in and look, how many anomalies did I have? Things that don't look normal. Okay, then I start going down that route, and I look at metadata around those connections. I look at SIEM logs related to those, web server logs, whatever else I need to do the analysis. But that's a way easier than looking at 10 different tools and 10 different, like you said, alerts and all this other stuff. So
I'm always of the approach of, and I think the term analyst means different things to different organizations.
Yeah.
To me, it's like you go to the ER, you're running triage, get them going as fast as you can. So to me, an analyst is the same thing. It's, I need to find that something bad likely has occurred. And then to me, I tag that off to incident response forensics teams. So like your tool where you're saying it's likely anomalous enough that someone should look at it, that's my trigger point for an analyst.
Right.
The fact that it's, Dridex versus Emotet versus like, I don't care at that level. I need to figure out, do I need to kick off incident response? Yeah, it looks bad enough. And then whether it's the same person with 2 different hats, I want them to at least transition those hats.
Right.
So it's very interesting. So how about you go into kind of demo mode, and we'll keep kind of talking through as you kind of showcase what you did, how it works, kind of your logic behind it.
Yeah, so I've got a Jupyter notebook that I wrote for this. So in the chat, those of you that are in chat, there's a bit.ly link there that I posted up, and I'll go ahead and do a screen share as well. And I'll
doing this. You're sending it to the panelists. I just resent it to attendees.
Oh yeah. Okay. Sorry about that.
Yeah, no worries.
So
trust the bit.ly link. There's no harm here, right?
No, I promise. I promise. Oh wait, there we are. Screen share. Man,
it's on
crazy technology. This over to the side. And where are we? Yeah, right here. Share that screen. All right. Can everybody see that?
Awesome. Yep. Your notebook's up and your bit.ly link's on the top right.
Yep. Perfect. So, and that should take you to, and it already should be built. If this doesn't work or we run into some issues, then, I told Justin I'm prepared to go ahead and jump to local. I've got a local instance of this running as well. So just in case the demo gods are not smiling upon me today, then we can pivot. But so anyway, in kind of the first stage of this, we're going to import the data. So, I told you that the data was gathered from the TLS Handshake. And I guess without kind of throwing out crazy question, if you've ever wondered what the TLS Handshake looks like, this tls.alfheim.net, and I'll throw this in.
Oh yeah, I might actually put this in 555. I think that's a more integrated breakdown of this than what I've got in class currently. That's neat.
Yeah, and this is a TLS 1.2. Down at the bottom, there is the TLS 1.3 as well, where he breaks it out like that. But what's really great about it, if you've never analyzed a TLS packet or looked at client the handshake, he breaks it down. So you can click on this and client hello, and there's literally the bytes of a client hello. And then, so you can look at annotations, and he breaks out the annotations exactly which byte offsets are what. So if you're doing low-level packet analysis of a TLS handshake, then this is like your go-to guide of exactly what bytes are what, how do you get that information, how do you figure out what's what. So
is there anything in here for mutual TLS handshakes? Or does it mark things as optional if it is doing mutual?
Yeah, it marks things as optional and everything else. So like you can see here on the 1.3, there's the wrapper, right? So, it's a smaller handshake process, only 3 steps instead of the full like 5 or 6 steps of 1.2, because it rolls things inside a wrapper here. So there's the full wrapper hexadecimal values, and then now it breaks down what happens inside each one. And then so anyway, this is a really great walkthrough, very, very detailed, as much in the weeds as you want to get to learn about that TLS handshake. So this, just kind of looking at my mindset as a whole, this was what I went to first, right? To try and understand this handshake process in much greater detail, to figure out what pieces of information might be useful. So if you look at just the client hello, we see, in a client hello on TLS, the client says, hey, here's the protocol versions that I support. And that may be, say, TLS, hopefully not 1.0 or 1.1, but hopefully it's a 1.2 or 1.3 that the client supports. Your web browser does this, right? And then it jumps to, there's a random data that's going to be used later in the handshake. That's going to be for key signing and that kind of stuff that happens later. You've got an optional session ID. So if one of the things that TLS does to cut down on this is it can generate a session ID. So if you come back later, it doesn't have to fully step through all the stages of the handshake process. It can say, you're already a trusted agent because you gave me a session ID that I recall or that I have in my database. So here we go. Let's bypass all this other stuff and reuse an existing key.
Just out of curiosity, when you were playing with this, did you ever see like malware or even like common frameworks like Meterpreter with Metasploit, where they'll use that optional SSID like right from the get-go as if it's already been stood up?
Oh, wow. Yeah, no, I did not. And I wasn't looking for it either, though. So
Sure.
When I was generating the data initially, I actually took about probably 60 gig worth of PCAP files and just extracted the TLS handshakes. So gotcha. I use tools like Cisco Mercury and stuff like that to just extract the handshake metadata for me.
Gotcha.
So since that's what they already do. So anyway, and this is what your web browser does every time it initiates a TLS connection, right? It just sends all of this data, and then the server responds with what it's willing to connect over. And, it kind of goes back and forth on this handshake process. So looking at that, I wanted to determine, is there any distinction between, anomalous, like say malicious connections versus your normal browser connections. One of the things, if you do get into TLS analysis, that you'll notice is that every time that Chrome and Firefox, and now that Edge is Chromium based, they come out with new versions or updated versions, they change that client handshake. The order of cipher suites may change. The cipher suites that are offered may change as they make things more secure or stuff like that. So that's kind of an ever evolving process. So that's one way. Let's say that the malware is using an older version of OpenSSL to encrypt traffic. Well, then that older version is going to offer up older unsecure cipher suites. It's going to offer up say TLS versions that are older and not as secure. So those are ways that an analyst can determine, is this something that's anomalous or not? And it's one of the things that the machine learning algorithm kind of looks at here. So first thing I'm going to do is import the data. And this data is just a CSV file of a whole bunch of stuff. I can show it to you, but it just looks like gobbledygook on the screen. So, but that's essentially what it's importing, is all of that data. I know that wasn't much, it just looked like a whole bunch of numbers, but we'll see it down here. It pulls it open and actually.
Assuming that's what came from Mercury?
Yes.
Okay.
Well, no, sorry. Actually, let me change that. No, so it's been formatted and normalized to be plugged into the database. So the data that came directly from my other, it looks like this, and it shows it color coded because it's just a plugin that I have for VS Code. Again, I know you can't really read that. It's really small, but essentially it's looking at the timestamp, the type, version, the message length, handshake length, all of that. It's looking at all of that metadata that can be pulled out or extracted from a TLS handshake. What I did then was took it and normalized that data and added in, if you see these, Tranco, there's a DGA, OTX, these are open source resources that I pulled in to do additional analysis and add into the machine learning data set that it was analyzing. So Tranco,
OTX, I'm assuming, is Alien Vault's Open Threat Exchange.
Yes,
DGA is Domain Generating Algorithm. What is Tranco?
Tranco is like the Amazon Top 1 Million, if you're familiar with that.
Mm-hmm.
It's used commonly in like domain allow and deny lists. Anything that's in the top 1 million, you're assuming that's the normal websites. The issue is that the Amazon top 1 million, actually several of the top ones, there was a paper that a guy wrote, that the team that did this, that came up with this Tranco, found out that those can actually be maliciously changed. How about that? Or influenced. So they came up with their own list that's not influenced in the same way because of like the Amazon ones and that kind of stuff. So
I have never heard of that. I'm learning all sorts of crazy things from you today.
Yeah, so like I said, it's purely security focused top 1 million. And the great thing about it, there's a Python module for it, where what I did for the analysis here is that I actually looked over the last 30 days and how many times within 30 days did that domain show up in the top 1 million. So not is it just show up today and it's good, because that top 1 million can change over time. So I created a count of how many times. And so basically this like 0.9333 right there is the statistics. It was 93% of 30 days, essentially, did it show up in that database. So that way it gives more of a statistical relevance as opposed to, just the binary. Is it there today and is it not? Because it might not be there tomorrow, that kind of thing. So, DGA is domain generation. These are Alien Vault OTX, URL host. If you've ever looked at that, trying to remember, I can't remember the domain name for that. Yeah. So the abuse.ch up here. Yep. So URL host has several different, they've got an API and stuff. So I checked their API to see, is it in their database, and then also looked at JAW3 and JAW3S just to round it all out because the community's, enamored with those. So I figured, why not? We'll just throw those in as well. So, and then now we get to the actual TLS header data. We look at the record type. We look at the TLS version, client version that's offered up. So like the 769 is actually the decimal version of the hexadecimal that's offered in the client handshake.
Hey, Bryan, can I ask you something?
Sure.
When you were going through this data, did you already know these things going into this project, or did you have to learn them?
I had to learn all of them on top of learning machine learning.
And I want to reference that because I think anybody who's watching this, their eyes might start rolling into the back of their head thinking, oh my gosh, this is impossible. And maybe this is a good point to stop real quick and just ask, like, from the point that you started this project to when you had it roughly done, what kind of timeline were we talking about?
4 months.
And 4 months, was this like a full-time job?
No. So again, it's working on my master's on top of my full-time job. So now I will say it was, and you can ask my wife, she'll probably say that I diminished the number of hours that I spent on it. But anyway, it was a lot of late nights. I will say that. But yeah, 4 months going from zero to, well, not zero. I understood TLS and basics of a TLS handshake, and I understood, basic packet analysis and that kind of stuff. But to this level, no, not at all. And practically zero about machine learning, except, everybody says it's the way of the future.
These are not the droids you're looking for. So would you say roughly 10 hours a week then for that 4-month period?
No. So the upfront, especially because the learning curve is fairly steep. I will say that. It was probably 5+ hours a day for about 2.5 months or 3 months of that. So yeah, 5 to 6, and then on Saturdays, Sundays, it may have been a full 8 to 10 hour day. Just focusing on this. So easily 40 to 60 hours a week just working on this.
Okay, so you did do this full time.
Yeah, I mean, yeah, I I couldn't tell which way was up and which way was down by the end of it, but
Gotcha.
So yeah, but like I said, I was still working a full-time job and working on this at night. So
gotcha. So that just for everybody, that's roughly 520 hours.
Gotcha.
So
not quite my 10,000 hours. So obviously I'm not an expert.
I always thought that's, to me, like, it's not 10,000. Is it 10,000? I thought it was just 1,000.
I don't know. I think it's
it might be 10,000. Either way, I feel like experience is learned by doing new things. If you do the same thing over and over, whether it's 1,000 or 10,000 hours, you didn't really learn anything. So for me, this is you in a constant evolution for 4 months this is one thing I found, and I'm pretty sure you're the same way. If it's new and you're challenging yourself and you've already committed to the challenge, the problem is you spend more time on this than you think because you're having fun.
Oh, I was.
Yeah.
Yeah. And now it is a lot of math. I will tell you that. So those of you who are math averse know that going in. There are a lot of things you need to understand about linear algebra, about tensors, which essentially a tensor, if you get into like the TensorFlow library for Python, are essentially matrices. So, so matrix algebra, that kind of stuff. You get into a lot of that. But
did you know that going in, or did you learn that or touch up on it?
I learned that throughout this process. I knew going in that it was going to be linear algebra and that was going to be, require stuff like that. But I intentionally wanted to do this without having to master all of those things first, if that makes sense. To kind of, to your point, was to be able to show that, yeah, you can do this too. Now some of the deeper things, if you will, right? There's some nuances to this that I'm sure had I fully understood all the math, I could have done better and could have done probably faster. But I was still.
And that's totally fair. But I'm asking these questions because I think people feel this is beyond them. Yeah. And generally, I think we feel if we can't do something exceedingly well, we shouldn't do it at all. And I love the mentality you went into this because, I was on a data scientist panel once, not where I was the scientist, but I had multiple like tried and true top-notch data scientists, and I was asking them questions. And I remember one was, do you feel that people have to actually have math degrees and advanced math knowledge to enter this? And they all kind of looked to the left, they looked to the right, and then they all head nodded and yep. And that was their answer. And I was like, I was so blown away because I didn't anticipate that, because I don't think that was intentional gatekeeping, but I think it scared everybody in the room and made them feel like there's no way, because some people aren't that great at math, but like one of my friends growing up, and I still touch base with him, he just quite frankly is not good with numbers. And I could give him something that people might say, oh, installing Zeek and Security Onion, that's easy. And it's hard for him. For whatever reason, his mind works in a really weird way, and it takes him 4 to 6 times longer than everybody else to do something. But he's stubborn enough, he can do it. And so I've seen him do things that if you were to ask anybody, could he do this? They'd be like, no, he's not smart enough to do it. And I feel like we in our community, we just need that stubborn tenacity.
Mm-hmm.
And I love the approach you went into this because, and I'm sure your wife would agree, you had a stubborn tenacity. I'm going to do it whether it kills me or not.
Yeah, pretty much. And I don't know how many times I wound up rerunning tests and changing parameters here and there just to rerun the same thing. And you've already seen playing around with it. Some of these don't run very quickly. Yeah. And when it's already 2 in the morning and you've been staring at it for 7 hours straight after working a full day, then, you know, it gets a little bit frustrating. But yeah, anyway.
Yep.
So we imported the data. And of course, as you can see, this is nothing but just a whole bunch of numbers, right? With column headers and stuff like that. So unless you are just a savant with these kinds of things, this doesn't make sense to the average person. So leveraging Python libraries, right? I was able to actually generate some graphs for this so that we can get a better understanding. And I could really kind of pick apart what those relationships look like in the data. So the first thing out was just to look at the distribution of malware. You see, it's a relatively small. I've only got 5% of this entire data set is known malware. So that was, I guess, another thing in looking at the data to put together for this is I had to find data sets where I knew what was malicious and what wasn't. So I had to train my model based on what I already knew going in, and then give it data that didn't have a label on it and see if it could make that determination on its own. So I intentionally kept the data distribution for malware small because that generates its own subset of issues in machine learning that I think I talk about here in just a second, just to kind of, when I start looking at a couple of the different models that I used, I'll talk through why that's a big deal. But so after that, right, so I've got a 5% distribution of malware. I said, you know what, that's good. I can mess with that. I can make that lower for some if I need to, or decrease the amount of benign traffic and increase the percentage of malware traffic if I need to as well. So I decided that 5% was going to be sufficient for my tests. So now I want to start looking at some of the cipher suites, right? So these are going to be when you talk about cipher suites in TLS, right? These are the different encryption algorithms, hashing algorithms, and things like that the client and the server say that they support as a part of that handshake process. So I wanted to graph the relationship on those. So now I'm just breaking it down and determining, okay, is there statistical relevance between these data points, right? Enough for me to be able to say, yes, a machine learning algorithm, like me as an analyst, I can look at it and say, yeah, there's a difference between these. So it's a whole bunch of Python code, but essentially what it's doing is generating these graphs down here. So the first one I see is just a count of the unique cipher suites that are offered. So it says that there were 34 unique cipher suites offered by the benign traffic, which we already saw is the major, 110,000 records are benign traffic. But the malware, which is a much smaller subset, only about 7,000 records out of that whole data set, has 133 different cipher suites. And that has to do with things like they're using older OpenSSL versions. They're using, basically they're using the tools that are available to write, whether it's C2 or to attach to their malware to encrypt communications and those types of things. So, and then browsers, right? Browsers are going to be pretty static. They're going to have those set ones. And unless there's a major update that occurs, then they're pretty much going to be the same across the board. I point this out because if you're a SOC analyst and you're wanting to look at some of the stuff without the benefit of some of the machine learning, that's one thing that you can say. Like you can look at all the cipher suites offered by all the browsers across your environment, and you can say anything that deviates from this, that's an anomaly, because these are all the different web talkers, all the different TLS talkers in my network, and they're only offering up these. So if I see something that deviates, now I've got something that's potentially anomalous.
In a way, this reminds me of the traditional threat hunting of user agents.
Mm-hmm.
It's just the cipher suite equivalent of it.
Yeah.
But do you find that the way you went into this helped? Like, one of the things I always saw with like user agents, where you're saying like, these are what our browsers use versus these are things we don't see, is just because you see something new doesn't mean an analyst should actually investigate it. But we kind of treat it as the traditional, what we would historically reference as whitelisting techniques, versus now it's an allow list. And
right,
they didn't scale well, because anything that was new was treated as an alarm when, as you mentioned, it's just an anomaly. But is it a significant, like, as you're going through and writing this out, was there anything in here, and maybe you're getting to this lower down, that would have like a significance level? Like, it's an anomaly, but I don't know if this isn't worth looking at, versus it's an anomaly and it's a high ranking, lots of deviation style anomaly. Or is that more where you have to take a look at, cipher suite plus this plus that, and you score off of that?
Yeah. So initially, and the model as it's built now is really just a binary decision. It's just a 1 or a 0.
Sure.
The stage that I would like to take it to is exactly what you're talking about, where it would give you essentially an anomaly score, right? Yeah. So closer to 1, it's yeah, there's badness here, right? If it gets all the way to a 1, it knows this is malware. But anything in between, any of those variations in between, yeah, it could be lower on the scale. It could be less likely that it is, that kind of stuff. I would actually have to change the machine learning model that I used, however, or change at least how it's implemented in order to do that. But that's kind of research-wise one of the things I was looking forward to make this, I guess, applicable or implementable, maybe that's the right word, across a broader range of data points and a broader range of environments.
Sure. Yep.
So we see just the number, right, of cipher suites is significantly different. And on top of that, we see that the top, like I laid it out down here, the top benign cipher, the C02F, that's the one that IANA designates as this TLS, ECDHE, RSA with SHA 256, right? And then, but the top malware cipher was a C014, which is a TLS, ECD, blah, blah, blah. So it's a different cipher suite. So not only was the number of cipher suites offered up different, but the ones that were offered the most commonly were also different. So it just shows an additional level of variance. Before I go too much further, I want to jump over to, if you've never checked out some of the TLS security parameters, too much, as outlined by IANA, they have a site at iana.org where you can look at the TLS parameters, and every one of these, from the client certificate type, cipher suite type, this was like a go-to reference, just like that Alfheim website for the TLS Handshake was as well, because this lays out, if you scroll down and look, you can see these are the actual IANA values that are associated. So when you're looking at the hex values of a TLS handshake, then these are the values that are going to be laid out. So now we've got TLS cipher suites. So I can scroll down and you've got right here, like a 0002, or the one that showed up down here is a C02F. So we can scroll down and we can find you can see there's a bunch of cipher suites. Maybe I can't see. what was it again? Now I'm losing my mind. C02F. It helps if you look at the right thing. So we can scroll way down. Okay, here's our C0s. And then we can find a C02F right here. So that's, I want you to, I'm pointing all of this out because I want you to realize I'm not making these things up, right? These are the actual values assigned by IANA. So if you're looking at raw hex of packets, that's what you're going to see is a C02F in the hex of the packets. And that's where this value comes from. So kind of putting all of these pieces of data together help you to kind of build a picture of what's going on and what's happening. So then we look at just simple things like port analysis, right? Like I said, I'm just looking at all the variations in the data itself. And we see here the the unique benign destination ports. It uses 1. Any ideas? Anybody have any ideas? I'm going to throw this out as a question. Maybe we can get somebody. Any idea what that port is? I haven't scrolled down yet.
You scrolled down a little too much.
Did I? Oh, dang, I did. It was given away. But let's see if anybody was paying attention. Maybe they were paying attention. Maybe they weren't.
I saw it. So
yeah, I know. I don't know if anybody else did. Anyway, so in case you didn't see it, it's port 443. We see the benign destination port is 443, which is your standard HTTPS or TLS port. But on the malware side, it's all over the place. There were 489 different destination ports used for the malware. And then source ports, again, we've got a 21% distribution across the 65,535 ports, but there's a 55%, almost 56% distribution, which means it used a much wider distribution. Because again, browsers are going to very commonly, they're just going to pick the same starting range, and many of them are going to pick the same starting ports and those kinds of things. So they're going to look fairly uniform across an environment, where malware can be all over the place. It's up to the malware author to make those determinations. So some of the destination ports we see are like port 25, SMTP. That shouldn't be TLS traffic on port 25. If you look at some of these and you do some of the analysis of, what was it? I think TrickBot uses 447 and 449 are some of the ports that TrickBot commonly uses for TLS. But anyway, the whole idea was to be able to show. Now, if you look over here on benign source ports, this is essentially, this graph over on the left is essentially what your network environment should pretty much look like when it comes to source port selection. It should be pretty uniform across the board. However, when you look at the malware, we're actually picking a source port of 443, which is an anomaly because your web browser doesn't use 443. It uses a random high ephemeral port, usually above 30,000, as the source port to go out to talk to port 443. So, that should raise red flags if you're not a web server inside the environment. So that
was crazy.
So that gets through kind of the data analysis. I did quite a bit more. If you look at the paper, there's some more graphs where I kind of lay out some of the different data relationships beyond. These were just some of the big ones that kind of stuck out in my mind to help me understand just the relationship of the data as a whole. But kind of stepping through this, it kind of led me to a couple of different machine learning algorithms to look at. And this is where we get into, I guess, kind of the machine learning part. Those of you that are here for the ML portion, I guess this is really the part that you kind of want to key in on. So we have 3 different algorithms that I use, or 3 different models. There's a support vector machine. There's a one-class support vector machine, which is just a variation of the SVM itself. And then I used an autoencoder neural network was the other one, was the third one. And the autoencoder I don't have demoed on the Jupyter Notebook. 1, it takes a long time to actually process the data, and 2, its correctness, is that the right word? I don't know. Its classification ability was limited overall. all. So so I wasn't, I didn't use it as part of the demonstration.
I always feel like this, like what you have from how a support vector machine works down to the bottom of the image. This is the stuff that always blows my mind when, like, if I have a data science book that I'm trying to slowly get through. But like when I first got it, all I did was I opened it up and I randomly picked like something in the middle, right?
Mm-hmm.
And I read stuff like this: support vector machine, hyperplane, margin, support vectors, nonlinear, kernels versus classifications, and then I look at the image like, oh, no problem, there's a picture. This will totally make sense. And it's like, nope, I don't understand a thing about that.
Yep.
So when you were learning, did you find like a lot of it is trying to first learn the terminology? That way you can even read what the heck this thing is saying?
Yes. Yeah, that was especially at the beginning. That was the biggest thing, was understanding the terminology. And you the ones you pointed out on here is actually just a very small subset of the terminology. I'm sure if you were to go to the beginning of the book that you're talking about, it's going to talk about a whole different subset of values that are on here. So
yeah, I feel like if I start at page 1, it makes sense. But if I skip ahead, it's just gibberish. It's like a foreign language, and it's super intimidating.
Yes, it is. And just know that if you're determined and you look at it enough and you see enough of these images and different representations and you actually do it, then
so we have a question from Daniel.
Makes a big difference.
Any good source of machine learning to start with, which I'm assuming is like books, training? Like, was there something that helped you? Oh, look at that.
I have a slide for that.
Fantastic.
Hopefully you guys can I'll even full screen it, make it bigger. So yeah, these were kind of some of my go-to. Now the Sec 595 is a brand new SANS course. I think Dave Holzer just beta tested that course like a week or two ago.
Mm-hmm.
So he's still, running through with that class and working out some of the kinks. But interestingly, his class, this Sec 595 class, follows along this an introduction to statistical learning with applications in R fairly closely, at least as far as the outline of the book goes and some of the different machine learning algorithms he addresses.
And I think it's funny because we talked about this in our first call, that you picked up a book on statistical learning with R, but you don't code or know R, right?
No, not at all. I did all the exercises that I did from the book. I did them all in Python.
And I have no clue about R, but I'm very interested in learning it with Python. Yet you would still recommend that be the book.
Yeah, even if you don't do the exercises, the book itself breaks everything down from the beginning, right? It assumes you're not a data scientist, but you want to learn about data science. And so it starts from, basic math stuffs, like, enough of algebra to be able to look at a linear equation and know, hey, okay, that's a linear equation. So it at least assumes that level of understanding. And then it allows you to kind of, it walks you through and holds your hand through that before it ever even gets to like machine learning and talking about specific models and algorithms and things like that.
Ooh, there's the second edition of that now.
Oh, nice.
All right.
So also this Toward Data Science is a really good site. There's a bunch of different blog articles on there, and those are very practical. They'll have a little bit of explanation what they're trying to do at the top, and then it's going to be a whole bunch of Python code after that. So I would recommend, if you're doing any of the Toward Data Science blog articles or things like that, to actually try not to copy and paste code. I know for me, I have to type it. Like I have to have one screen open over here and, VS Code open over here. And I actually have to type it in, because then I have to troubleshoot it when I mistyped it, right? Which means I also have to understand how the code is working. So I know at least my mental processes require that. So The same for the machine learning mastery. He's got a lot of different source code examples, a lot of Python code, stuff like that to walk through. And then medium.com, if you just start looking up, machine learning for some of these, then anyway, and if you're into the dad jokes and just the silly kind of stuff, Josh Starmer has a great StatQuest YouTube channel, and he like writes songs for everything, and they're cheesy songs about data science, but it does make it fun. So,
like it.
Yeah,
Awesome.
so those are my go-to resources. So hopefully those can help you. If you need that backup or whatever, or just that slide, then let me know. I can post that in the chat or
maybe at the end. And I'm going to post this on YouTube when we're done, and I'll probably try to put links to some of those in the description.
Cool. So support vector machines, right? We're talking about an SVM. This was kind of the foundation of the two primary models that I used. So you brought up things like a hyperplane. Really, honestly, a hyperplane. So in this instance, we're talking two-dimensional space. I've got the above the line and below the line, or basically the orange squares and the blue circles. And so basically what the support vector machine does is it's analyzing the data in order to classify. So it's called a binary classifier. And essentially it's assigning like a 1 or a 0 so that it can group and separate those values from one another. So just like we stepped through and looked at those graphs and came up with there are differences. We understood that the support vector machine actually creates those mathematical representations of the data. And then it draws this hyperplane in between, right? It puts a separating line in between based off of what they call these support vectors. And these are the closest values to one another. And so it finds that midpoint between that so that it can actually essentially create this delineating line between the data. Okay, and then it creates this margin based off of these support vectors. So the hyperplane goes right across the middle. So it's just a fancy way of saying a line. If we're talking two-dimensional space here, is what a hyperplane is. The issue becomes, and let me scroll back up just a bit here to the top. In machine learning, I have it printed out the data here, right here. I have 116,000 rows and 519 columns. So for machine learning, if we were to try to graph this, then it would be a 519 dimension graph.
Sweet.
So each column essentially would be a different data point on a different dimension within the graph. So obviously we can't graph you can't visualize 519 dimensions.
Come on, Bryan, speak to yourself.
So what I had to do then to be able to visualize how the support vector machine is working is actually condense it down to 2 dimensions so that now I can get a visual representation of how this data relates across 2 dimensions, and I can draw that hyperplane and the margin around the data. So we see one of the first things we see from this is it's not linearly separable, if that makes any sense. I can't just draw a single straight line in between it and separate one data up here and one data point down here. I had to draw this circle around it, meaning that it's not linearly separable. So that's where you brought up the term kernels. That's where these different kernels come in and allow me to treat data differently. Because if I were to separate this with a single straight line, that line would probably be, I don't know if you can see my mouse pointer right there, but it would probably go right down the middle there, because that creates the closest separation, but it also separates known good, all the blues from one another, right? So we can't properly define relationships between that data without using one of those.
So if I'm looking at this, so then are the kernel classifications the rings, like inside each of the circles, the concentric circles?
Yeah, no. So the kernel tells it what type of shape to use.
Okay.
right?
Yeah.
Whether it's a polygon or it's an oval or a circle or whatever. Those are kind of what the kernels define is how to treat the data.
Okay, and then in here, what do the colors represent?
So the blue represents the benign traffic and the green represents the malicious traffic.
Gotcha.
And
what about the black circles?
Black is where black are the support vectors.
Gotcha.
So the way that I graphed this was that it would put a black circle around all of the support vectors to show which measurements it used to determine this particular shape.
Okay.
And when you see a whole bunch of them, like the black section, that's just a whole bunch of support vectors all right on top of one another. So the solid line is our hyperplane, and then the dotted lines show the margin, because the margin was defined by these support vectors. Does that make sense?
I mean, if I'm being honest, I'm lost.
You're lost.
I'm lost. But again, I'm not a data scientist. Like I've probably only read like 20 pages of stuff. So I'm in my infancy stage right now.
I got you.
I think I was following you all the way up until you got here. And I think what I'm struggling with is there's so many new terms that I don't like. There's a picture, but I can't map the picture in my head to the terms because I don't know the terms yet.
Yeah, so think about the classes as a 0 and a 1. Okay. So let's say our orange squares are a 1 and our blue dots are a 0.
Okay.
So how much those 0 and 1 values are separated from one another. So let's say our hyperplane is 0.5. It's drawn right across the middle because we know 0.5 is a proper separation, an equal separation between a 0 and a 1.
Yep. Okay. Yep.
And and my support vector, my margin, right, is basically just what it shows how separated those values
in a perfect test. Then your margin is going to be 0.5 in both directions.
Correct.
Okay. Gotcha.
Exactly. So now what we did is we took those 519 different dimensions and we used a different. This PCA, which is oh my goodness, I cannot remember. I just went completely blank. What PCA stands for? It's
personally careful algorithm.
Principal component analysis is what it's called. Anyway, it's a form of reducing the number of values, the 519, down to a smaller value. So I told it the number of components to use is 2. So now in this case, I've got a 0 and a 1. I'm telling it I only want a 0 and a 1 output. Those are the only options. So now it finds the mathematical representation of each row, right? Each row is a sample or a TLS connection. And it looks at that and it calculates it mathematically. And it says, is this a 0 or a 1? And then it looks at row 2. Is this a 0 or a 1? And it does that based on how they relate to one another. Does that kind of help?
Yep. No,
so
I'm
now
tracking that.
Yeah, and so now we get down here and we see that it's not, I can't just draw a single straight line through it. I had to draw this oval type shape around it in order to be able to create a hyperplane that separates my 1s from my 0s.
Gotcha.
Does that kind of help?
Yep. No.
Okay. So this is what the support vector machine does. Now the problem you run into, remember, I said that I've only got a 5% malware distribution out of this whole huge data set, 117,000 records or TLS connections roughly. Well, if we see here over on the left picture, this is a standard support vector machine. The blue line is the support vector machine trying to draw a hyperplane, but because there's so many blue dots and not very many red dots, it doesn't quite know how to place the hyperplane. There aren't enough of those support vectors to create a proper margin so that it knows the best place to put it in. Does that make sense? To separate these two. To us, it looks easy, but the math algorithm that's being used, it's confused. So we use what's called a one class support vector machine. So in this case, the one class, we only use the benign data to train the system. Okay, So all of these plus ones out here, all of these are our benign data points.
So in my mind, that's basically where I'm saying, hey, kid, draw the line to separate the blue from the red.
Yeah. Yeah. And it's one of those kids that thinks outside the box.
Okay. Oh, yeah. Okay, I see what you're saying. Yep.
But the one class, now we're saying, look, all of this stuff is good. We know this is good, and we're training it really well on what's good. So then anything that happens that doesn't look like the good stuff, that's the negative ones down here. And it classifies it. Here's this hyperplane. So it says all of this bunched up here is good. And we're just going to draw a line and say anything below the line mathematically is bad.
Gotcha.
Okay. So it's just a different way of approaching this problem for the support vector machine. So as we go through and we train our model, oh no, what happened? Uh-oh, give me a second.
It might be from one of your restarts of the kernel.
Yeah, I think so. I got to go back up and rerun a couple of these. It's what happens when you talk too much and it wants to try to time out and conserve resources. Psh, what's it thinking?
Yep.
Resources, shme sources. Let me see. I can't remember if I did anything else before that. I think that was it.
So yeah, okay, let's go on. I'm curious, as you were going through learning this, I'm assuming your focus initially was just getting it to work.
Yes.
Rather than optimization.
Yes. Very much so.
I usually code to make things work, but then I know like running this type of stuff on CPU versus like GPU, huge difference. Plus, probably 90% of the time when I write something, I have to redo the math because there's a much more efficient way, regardless of where it's running.
Mm-hmm.
I don't know.
But so honestly, the when you talk about code optimization, the biggest thing that it took me forever to figure out was actually how to generate the initial data set for me to analyze with this. And I spent more time on that in probably 2 full weeks just on that alone, because I had so many records. I had 120,000 records, and I'm having to get open source Intel data on every single record. I'm having to build all of these relationships across about 3 different files because it wasn't all in one file. And so that took probably 4 days running. So I had to learn multi-threading in Python.
I was just about to ask you, were you playing with multi-threading and multi-processing?
I was. So I've got a laptop. I've got a 6-core i7, and with hyper-threading, that gives me 12 cores. I was using all 12 for 4 days straight just to generate that data. So that would be the most painful part of it.
Sure. And I definitely buy that, because one of my friends, Austin Taylor, he is a data scientist, and he does data science classes at like Black Hat. And he's like, in every class we talk about data manipulation, handling, and because before you even get to all this stuff, you got to get the data in the format with all the enhancements you want. Otherwise it doesn't work.
Yep, exactly. So, okay, so we've trained our model. We've imported a data set of roughly 50,000 records of all benign traffic, and I'm going to train it with that data set. So this is just the Python output from the training. And so now we need to look at some different score values. We have to have some way of determining how well this classified data for us, essentially. And we're doing this on the bulk level, looking at kind of all of our data sets together. And so let's see, there was a question in the Q&A. Did I miss that, or?
Yeah, so Francois is asking, is there a prerequisite to this? I just shot him. Are you referencing prerequisite to the webinar or things you should learn before trying to dive into this level?
Yeah, and if we go back to this and you start with this introduction to statistical learning with applications in R, it's going to give you a lot of those prereqs. It's going to help hold your hand through, and you'll see fairly quickly if you don't understand the math, then that gives you an area that you can kind of go back and research and kind of get spun up on some of that stuff before you kind of come back to it. So you'll figure out fairly quickly, you know, what parts of it don't make sense and what parts you need to go learn a little bit better.
Yep. All right, Bryan, you've got 5 minutes to finish up.
5 minutes. Holy moly. All right. No, we're good. So we're right at the end, right? We're just looking at how we score this because you have, you know, true positive, true negative, false positive, false negative. If you've ever looked at like IDS, IPS alerts and stuff like that, you're familiar with this concept of true positive.
Painfully.
Yeah. So machine learning, we're using the exact same types of things, but we have different ways of measuring this analysis. So we look at precision versus recall versus accuracy. And then there's this F2 score, which is just basically a combination of precision and recall that's weighted toward the false negative. So essentially, I would prefer something to be false positive than false negative, if that makes any sense at all to you. Because let's say our machine learning looked at it and thought that it was malware, but it wasn't. So it was a false positive. Well, I would rather that than it thinks it's not malware and it really is, which that's the false negative side. So I calculated the F2 score to compensate for that because I wanted everything weighted toward that false negative measurement. That was more important in my mind than the false positive.
Gotcha.
So we come down here and we calculate our scores and we see we've got a 99.35% accuracy. We've got a 100% precision, which we look back up here at the precision was the true positive over the actual results. So this is how the machine learning algorithm is kind of measuring this stuff. It's like, I know based off of my labels, this was positive and this was negative. So I'm comparing that to how the machine learning algorithm actually predicted those values. So we see like on this graph right here, this is called a confusion matrix. We've got our predicted on one side and actual on the other side. That helps us to determine what that output looks like. And then the recall was a 99 and we've got our F2 as a 94. And we've got the graph down here to actually show what that looks like for you. Don't worry about the rock curve on the right, but that confusion matrix kind of maps out. We've got so we have a 0, over here in the low left. We see on the left-hand side is our true measurement and the bottom is our predicted measurement. So it was predicted malware and it actually is malware. We got 100 records. It was predicted malware, but it was actually benign. We had 99 or 91 false positives. But if it was predicted, if it was actually benign, is the true, but the prediction was malware, we have a 0 false negative. So again, I'm okay. Personally, I'm okay with that because I'd rather spend some time maybe getting to know a little more intimately, like Justin was saying, what's going on or what's right or wrong in my network, and trust that whenever this thing says something is benign, I know it's a good, an accurate measurement. So,
yep.
So anyway, that's the end of at least the Jupyter Notebook and the show and tell. I hope that answers kind of your questions. I know there's probably a lot, again, coming from 0 up to this. I know there's a lot that I had to leave out, but we do have kind of a condensed timeline here. So
no, and I think for what I was hoping out of this, I think we've achieved. Like you've showed your logic and how you're putting this together, what you're trying to train, what you're trying to build, how the numbers, like, I don't think everybody's going to understand when they watch this video, maybe everything that's happening under the hood, but I don't think that's the point. To me, the point is this stuff does work. And whether I'm being optimistic or not, believe anybody who's willing to put the effort forth can technically pull this off. Mm-hmm. Now, for you, it was 4 months of close to full time. For others, that might be a year plus. And I'm not saying everybody needs to do this, but to me, you're kind of like the shining light and hope in the dark that it's possible.
Yeah.
And whether or not you should, you need to figure out where your job and career and family's going in life, but it's possible. And that to me is, I don't know, it just gives me hope.
Yeah, and I agree. And I don't know, when you look across kind of the CS community right now, right, especially if you look on the commercial side, it's supposedly, right, I mean, this is where everything's going, or at least commercial keeps pushing, right? AI is going to solve all of our problems. It's going to fix everything. And, you just set it and forget it, and it just does its thing. Well, no, really it doesn't. And we don't know that as practitioners until we can kind of spend some time in the weeds and trying to figure some of this out on our own. So that now we can go into meetings and talk intelligibly. We can start asking data scientists, well, what algorithms are you using? Is this, how are you classifying this? What data are you actually looking at that I need to provide you? And I mean, I've been in some of those meetings and they just say, the more data you give me, the better. Well, no, not necessarily. I can give you a whole bunch of garbage data, but it doesn't mean, and then what are you doing? You're detecting garbage. So, the better we can make those interpretations, then, the better that we're all going to be in the end, I think.
Absolutely. Absolutely. Well, we're technically almost 15 minutes over.
Sorry about that.
No. It's because it was a good conversation. I like it. We do have one more question I see. Would this be used to continually digest TLS data to learn new trends? Like what if new malware trends are very similar to benign traffic? Wouldn't the probability of false negative increase?
Yes, it actually would. If you were to use this over a long period of time and malware authors got smarter and started using, more updated libraries and stuff like that. The difficulty becomes, as I said, when Chrome is updated and Chrome now uses a different TLS handshake, then the malware author also has to go back and update his malware so that now he continues to look like the Chrome web browser in your environment. So that does help. That is good for us as security practitioners that's the case. So
no. Okay. Well, this is going to be posted on YouTube for any of your friends who are wanting to attend, or if you're wanting to reanalyze this. As always, you can feel free to email me afterwards, and I will gracefully ignore questions I don't know how to answer. But Bryan, thank you so much for joining on this, and well, from learning this from scratch and putting it together, it seems to me to be a really cool project. We'll probably talk later about possibly bringing this in, maybe even as a lab in 555. I still think that would be awesome. And other than that, everybody, thank you for attending, and we'll all stay in touch.
Sounds good.
All right. Thanks, Bryan.
Yep. Thanks.
Bye.